In this paper, we explore how new web technologies, WebAssembly and WebGPU, can be used to deploy powerful visualization solutions for large-scale scientific data that run entirely on the client in the browser. We evaluate the programming effort required to bring scientific visualization applications to the browser through these technologies and assess their competitiveness against classic native solutions. Specifically, we evaluate the use of libtiff via WebAssembly for importing microscopy data, the use of loss tools via WebAssembly for LiDAR visualization, WebAssembly and WebGPU for serial and data parallel isosurface computation, respectively, and parallel decompression of volumetric data with ZFP through WebGPU. As a main example, we present a new GPU-driven isosurface extraction method for block-compressed datasets that is suitable for interactive isosurface computation on large volumes in resource-constrained environments, such as the browser. Here we show an illustration of our parallel isosurface algorithm in 2D. Starting from an existing cache used to compute a previous surface, or an empty one, we wish to compute the surface at the new ISO value, shown in A. In B, we find the blocks that contain the ISO value, or are needed to provide neighbor data for the blocks containing it. In C, we determine which of these blocks are already in the cache, and those that must be decompressed and added to it. In D, the active blocks are filtered down to just those that will output vertices. In E, we perform a prefix sum and stream compaction to compute the IDs of the blocks that will output vertices. In F, we compute the number of vertices that will be output by each block, and finally in G, output them to a single vertex buffer. Please see the paper for more details about the algorithm. Here we show interactive isosurface computation on the 512-cubed plasma dataset using our GPU algorithm run on the integrated GPU of a Surface Pro 7. The original data is 537 megabytes and is compressed to 1/8 of its size. Volume blocks are decompressed using ZFP, cached, and isosurfaced on the fly. The web page also displays the number of blocks that were newly decompressed and cached to compute the current isosurface, the number of blocks that potentially contain the surface or are required by neighboring blocks and are thus active, the number of these active blocks that will actually output vertices, and the number of cache slots that are available. Here we show interactive isosurface computation on the 832 by 832 by 494 stag beetle dataset, also run on the Surface Pro 7. The original data is 1.37 gigabytes and is compressed to 1/16 of its size. Here we show interactive isosurface computation on the same plasma dataset as before, now run on an RTX 2070 GPU. Here we show interactive isosurface computation on the 1024 by 1024 by 795 Kingsnake dataset, run on an RTX 2070. The original data is 3.33 gigabytes and is compressed to 1/16 of its size. Here we show interactive isosurface computation on the 1024 cubed Miranda dataset, run on an RTX 2070. The original data is 4.33 gigabytes and is compressed to 1/8 of its size. Here we show interactive isosurface computation on the 1 terabyte DNS dataset run on an RTX 2070. The original data is 1 terabyte and is compressed to 200 megabytes. After making the appropriate resolution and precision trade-offs, our GPU-driven isosurface extraction algorithm makes it possible to interactively explore this dataset entirely in the browser.